Okay, so starting section 5.1, 5.2 lab, going over these solutions, we had a question about problem number 1, which is basically the question. The question is, how are they different? Which grows the fastest? Which grows the slowest? Your question was basically, if you graph all of these at the same time, how do you know which is which? We discussed this a bit in the last class. Sorry, guys, I dropped my pen. Where if you look at the base of the exponential function, you can determine if you have an exponential growth or decay. And if you graph several exponential functions together, the bigger the base, the steeper the curve. Or a bigger base means that your graph is growing faster. We looked at several problems like this last class. It was like 2 to the x, 5 to the x, 10 to the x, I think maybe 20 to the x, at like 5 different exponential graphs. And we saw that they all had the same general shape, but when the base got higher, the graph increased faster. So it was a steeper curve. Or you can think of it as like the top part is closer to the y-axis. So that's how you can determine which graph is which. So first, what do all of these graphs have in common? All graphs are increasing. They all have a y-intercept at 0, 1. They all have a domain of all real numbers, or negative infinity to infinity. And they all have a range of 0 to infinity, all positive numbers. They also all have a horizontal asymptote, which I usually just abbreviate HA, but let's write it out. Horizontal asymptote at the horizontal line, y equals 0. That's the x-axis. So this is true for all of these functions. How are they different? The only thing that's different is how fast they're growing. 9 to the x grows faster than 5 to the x and 2.5 to the x. 2.5 to the x obviously grows the slowest. And then it's asking which graph is the steepest. The higher the base, the steeper the graph. So y equals 9 to the x is the steepest, and y equals 2.5 to the x grows the slowest. And just really quickly, we'll graph all 3 of these together. 2.5 to the x, not 2 equals 5, 2.5 to the x power. What was the other one? 5 to the x power. And last one is 9 to the x power. Okay, and as you can see here, even if this weren't there, if I didn't see those graphs and know which color matched with which, just by knowing that my biggest base is 9, I know that this green curve, the steepest one, should be 9 to the x. Next steepest would be 5 to the x, which is the blue curve, and the last, or least steep, would be 2.5 to the x, which is the red curve. All right, then on to B. Graph 3 to the x and 1/3 to the x on the same coordinate system using technology. What do all the graphs have in common? How are they different? So again, both graphs here have the same domain, range, intercept, and asymptote. Both graphs have a domain, negative infinity to infinity, range 0 to infinity, y-intercept 0, 1, horizontal asymptote. Oops, it's a line. Y equals 0. What's different? Y equals 3 to the x increases, or is increasing, I should say. And y equals 1/3 to the x is decreasing. So one is an exponential growth, an increasing function, and the other is an exponential decay. Remember, if your base is between 0 and 1, you get a decaying or a decreasing function. All right, and then part C, sketch, we should look at these graphs also. Let's be thorough. 3 to the x and 1/3 to the x. There's 3 to the x, our exponential growth, and then 1/3. Okay, to the x power. So as you can see with these two curves, one is increasing, one is decreasing. They're actually reflections of each other. So if you take the purple line and reflect it across the y-axis, then you get the black line, okay? So they're kind of opposites of each other in that way. But they both have the same domain. You can plug in any value for x. You can only get out positive values for y, so same range. Both cross the x-axis at 0, 1. And both have horizontal asymptotes at the x-axis. However, for 3 to the x, you start off with very, very small numbers close to 0 and then get bigger. For 1/3 to the x, as x gets bigger, the graph gets closer and closer to 0. So the asymptote's on the other side, but still the same asymptote. Part C. Sketch the graph of y equals 5 to the x and y equals -5 to the x and explain how you can obtain the first graph from the second. So we can go look at these on Desmos, but if you take a function, any function, and negate it, that means you're just like negating all of the y values. So you're reflecting the graph across the x-axis. So we would say the graph of y equals -5 to the x is the graph of y equals 5 to the x reflected across the x-axis. So we'll go to Desmos in a minute, but even without Desmos, we would say this is x, this is y. We know that 5 to the x is a growth function, so it would look something like this. That's 5 to the x. Then -5 to the x would just reflect this across the x-axis. Let me get a picture that looks like this. All right, and let's verify that graphically. 5 to the x, -5 to the x. They switched the colors from how I did it, but as you can see, the graphs are just reflections of each other over the x-axis. Then on to problem number 2. I need my calculator. Suppose you invest $30,000 at 3% annual interest compounded continuously. Write the equation that will model the growth of the money. So the equation would be S equals our principal, which is 30,000, times E, and this is growing compounded continuously, so we have S equals P e to the RT. So 30,000 times e to the 0.03 t power. We plug in t, the number of years, and this function will tell us how much money is in the account, or how much money we've earned from the investment. Find out how much money will be in the account after 10 years. Write your solution as a complete sentence. So if you plug in 10 for t, let's see what we get. 30,000 times e to the 0.03 times 10 is $40,495.76. So this would be after 10 years, the account has $40,495.76. And remember, we have 2 compound interest formulas. We'll see those again in chapter 6. When you see continuously compounded, that's where you use the one with the E. Then on to problem number 3. Look at this fun one. Problem number 3 says, a new restaurant keeps track of the number of nightly customers at monthly intervals over the course of a year. The restaurant has done very little advertising, but it's most of its publicity is by word of mouth, but its number of customers is increasing. The restaurant does not have a seasonal difference in number of customers. So for example, there are no summer crowds. Using the data in the table, fit an exponential regression model, C of M, where M is the months and C is the number of customers. And then we're going to use that model to estimate when the restaurant has 400 people, and then use the model to predict that when the number of nightly customers will be 18. I'm sorry, what the number of nightly customers will be in 18 months. Okay, so from the table we see when they first started tracking this at month 0, there were about 35 customers. After 4 months, they went up to 66 customers. After 8 months, 141 customers. And after 11 months, 275 customers. So we want to come up with a regression model. We're going to do this in Excel. All right, so in Excel, basically you just want to write your inputs in one column, your outputs in another column. If you want your graph to have labels, you should put labels at the top of each column. So for us, the input was the month. So if we type in months here, and then the output was the number of nightly customers. So if we type in customers here, then when you graph your function, or graph your points, I'm sorry, it'll label the x-intercept and the x-axis and the y-axis. All right, for the months, we're going 0 to 11. I messed that up already. 0, 1, 2. Of course, we can do this quicker in Excel if you select and then drag. I might have done, okay, 9, 10, 11. Boom, there we go. 0 to 11. And then for the customers, just be careful as you're entering in the numbers and make sure you don't have any typos, because if so, that'll change your final answer. 46, 54, 66, 84, 103, 117, 141. Oops, see, typo. 141. Why won't enter work? Enter. Where are we? 9, 180. And then 222 and 275. Okay. And then always just go back to double check the information that you have entered in. All right. I don't think I have any typos. Then to find your regression equation in Excel, you select all of your data, go to Insert, and then over here at Charts, click on the one that looks like a scatter plot. So the first one, you don't want anything connected. And as we plot these points, hopefully we can see that they are slowly increasing and then start to increase quicker. So this kind of looks like an exponential curve. That's why we want to model this with an exponential function instead of, say, a linear function. Okay. Now, to find the actual exponential curve, you want to right-click on one of the points. And then at the bottom here, it says Add Trend Line. That'll give us our regression equation. All right, and from here, if you go over to the side here where it says Format the Trend Line, you can pick what kind of trend line you want. Trend line does not mean line. So you can choose whether you want, it's a curve. Do you want a linear function, an exponential function, a polynomial function, a logarithmic function, and so on. Right now it's a line. We don't want that. We want exponential. So this is what the exponential curve would look like that most closely fits these data points. And then if you scroll down, we have to click Display Equation on Chart so that we actually get our equation. I'm going to move it up and then zoom in. Can we make it bigger? It won't let me make it bigger? Terrible. All right, so I'll zoom in here. Our equation is y equals 32.485 e to the 0.1893x. So let's write that down for part A. All right, now some of you may know how to do this regression using your graphing calculator. If you wanted to use your graphing calculator, you could do that. I find that it's easier to me to do it with Excel. And also I like to use Excel because in practice, like in life, I don't know if you would have a job that's going to ask you to pull out your TI-84 to do any work, but you'll definitely have a job where you need to know how to use Excel. So being able to practice these things in Excel is nice because Excel is something that you'll actually use and practice in your careers and in life. Okay, so for part A, we found the regression equation. It was 32.485 e to the 0.1893x. And then we're asked to use the model to estimate when the restaurant will have 400 people. Okay. Now to do this, this is saying we want to know when 32.485 e to the 0.1893x, we want to know when this is equal to 400. Okay, so we want the output to be 400. We are going to learn, probably by the next class, how to solve something like this algebraically. But for right now, we can solve it graphically by letting your graphing calculator, y1 equal your equation, let y2 equal 400, and then find the intersection. Okay, so we'll do that in Desmos. Let's see, we have 32.485, where's E? E to the 0.1893 x power. So an exponential growth function. Notice we can't see the top of it. The next one I'm going to have y equals 400. We're going to have to change our window so that we can see the intersection point. There we go. And if we click here on the intersection, we see that the intersection happens at about 13.26. So this is after about 13 months. Okay, let's write that up. Usually when we solve something graphically, we like to sketch our graph. I'll come over to the side and do it here. Move out of the way. All right, so we had, this is X, this is Y. Our graph was an increasing exponential function. And then we had a horizontal line here, y equals 400. And we got that this intersection point was at about 13.2 comma 400. Okay, so what does this tell us? After about 13 months, the number of customers will be 400 people. Okay, that's our answer there. Now, again, this is solving an exponential equation. This is how we would solve this graphically. Also, if you did this in your graphing calculator or put this into your graphing calculator, you could scroll down the table to solve numerically. And we'll talk about how to solve something like this algebraically in the next couple of classes. Okay, part C, use the model to predict when the number of nightly customers in 18 months. So here, X is equal to 18. We'd have Y equals 32.485 e to the 0.1893 times 18. Okay, and that would be, we're talking about nightly customers, so you can round to the nearest customer. So I would say this rounds to about 981 customers. Okay, and then last part, what does the end behavior of this model predict? As time, the number of months increases, what is happening to the total number of nightly customers? And then do you think this model is reasonable? So let's look at the graph of this function really quickly. We want just 32.485 e to the 0.1893 0.93x. What is happening as time goes on? If we trace this graph, as x increases, the number of nightly customers increases. Right? Look at the outputs, 300, 400. It's going to keep on going up forever and ever, and keep going up forever and ever. So if you kept doing this after 10 years, it'll say that the nightly customers keeps going up and up and up and up and up. So the end behavior is showing as the months increase, the number of customers is going to increase. But can the number of customers just keep increasing exponentially forever? Is it possible for them to serve 1 million customers in a night? Well, that would have to be a pretty big restaurant, lots of chefs, lots of stoves. So this model may work for the short term, for like a year for tracking customers, maybe for 2 years. But ultimately, depending on the size of the restaurant and, you know, time and the number of people, there's going to be an upper bound. This won't be a reasonable model in the long term. So to answer this question, oops, sorry about all the scrolling. What does the end behavior of this model predict? As the months increase, the number of customers will increase. And do you think this is a reasonable model for the long term? This is not reasonable for the long term. And again, why is it not reasonable for the long term? Well, because eventually there's going to be some bound on the number of customers that the restaurant can serve each night. So it can't just increase forever. And then the last part here, my favorite, what is the growth rate of this regression model? So we got this regression model up here, 32.485 e to the 0.1893. Which one, what number here tells us the growth rate? The exponent. Remember, we have for R is 0.1893. And if you write that as a percentage, that's 18.93%. So this is saying that the number of nightly customers is increasing by 18.93% per year. All right. All right, you guys. So we are going to pick up with our discussion that we were having in last class, section 5.2, which is on logarithmic functions. And today we're going to practice going back and forth between exponential form and logarithmic form of an equation. And then some properties of logarithms that we should know that will help us simplify and evaluate logarithmic expressions. And there's one more thing. Oh, something called the change of base formula and how to expand and condense logarithms. So we'll finish up the rest of lab 5.1, 5.2, and then your lab for today, lab 5.2, we'll have more practice problems like problems 4, 5, and 6 on there. All right, so this is still section 5.2. And this section is over logarithms. And remember, last class we talked about how logarithms are the inverse of exponential functions. Basically, with logs, there's a base, just like with an exponential function. The difference is, with logarithms, we know the base and we know the output. The logarithm tells us what our exponent should be to get that output. So if we have y equals log base A of x, then this is the same as saying that A, whatever your base, I think we're using B for our base, sorry. I guess it doesn't matter. A to the x power, I'm sorry, A to the y power. Why is everything deleting? There we go, let's start over. Y equals log base A of x. Your logarithm has a base, your exponential expression will have a base also, they'll be the same. So if y equals log base A of x, then this is the same as saying A to the y power equals x. So notice where these three parts go. First, the base of the log is the same as the base of the exponential equation. This is the important one. What the logarithm is equal to. That is your exponent. So the logarithm is telling us what our exponent should be. All right, so whatever the value of the logarithm is, the output, that's telling us what the exponent should be in exponential form. And then the last thing, what you're taking a logarithm of, that's what the output should be in exponential form. So we're going to practice a little bit going back and forth between logarithmic form and exponential form of some expressions. And then we're going to also talk about how we can use like what an exponent or what a logarithm means to evaluate some easy logarithms. All right, so example 1, we want to write the log equations in exponential form. And we'll do 3 of these. The first one, we'll do log base 4 of 1 over, let's make it easier, of 64 equals 3. For the second one, we'll do log base 2 of 16 equals x. And then for the third one, let's go log base b of g equals n. Just made that one up so we can practice where do all of these parts go. All right, so when we write these in exponential form, first, we know that the exponential equation is going to have a base. Whatever the base of the logarithm is going to be the base of the exponential function. So here, the base of our logarithm is 4. That means we're going to have an exponential expression with a base of 4. All right, boom, the bases are the same. Next, whatever the logarithm is equal to, that's what our exponent should be. So here, our logarithm equals 3, then the exponent should be 3. So we have 4 to the 3rd power. And if log base 4 of 64 equals 3, that's just telling us that 4 to the 3rd power is equal to 64. And that's true. 4 to the 3rd power does indeed equal 64. All right, on to part B. Log base 2 of 16 equals x. Our base here is 2. The logarithm is equal to x, so that means that our exponent should be x. And then the output is 16. So this is what logarithms are for. We're trying to solve basically an exponential equation. What power would I raise 2 to get 16? That's what this is asking. Okay, we will be able to solve ones like this without a calculator by the end of class. Okay, but that is the exponential form. So saying log base 2 of 16 is x, this is the same as 2 to the x power equals 16. All right, and last one, log base b of g equals n. The base is b. The exponent would be n because the logarithm is equal to n. And then b to the n should be equal to g, according to this logarithmic form. Every single log equation has an equivalent exponential equation. And you should be able to go back and forth between the two. And in practice, you'll see this in the next class and maybe at the end of class today, depending on how much time we have. You'll see how using the exponential form can help solve logarithmic equations, and using the logarithmic form can help solve exponential equations. In the next example, we're going to go the other way. So I'm going to give you an exponential expression, and you want to write it in logarithmic form, or an equation, I should say. All right, example 2, we want to write the exponential equation in logarithmic form. And we can do 3 of these also. All right, let's go 3 to the negative second power equals 1/9, because that's true. Let's go 5. Oh, I think we have this one on our lab. To the x power equals 125. And then for the last one, let's just b to the x power equals, what do I want to call it? M. Okay, doesn't really matter. Okay, so these are all exponential equations. For the first one, we know all of the values. We know the base, we know the exponent, we know the output. For the second one, b, that's an exponential equation where we're trying to solve for the value of x, which is the exponent. And then the last one, we just have variables for all of our expressions. For all of these, we can write them in logarithmic form by remembering. Also, as I'm saying this, I keep repeating the words as, or reading the logarithm as it should be read. That will help you when you're writing your logarithmic expression. For example, the base of our exponential expression is b. You should have log base 3. I'm sorry, I said b. The base of the exponential expression for part A is 3. So we should have log base 3. How do you write that? You write the word log with a subscript of 3. Okay. What are we taking the logarithm of? Whatever the output is for the exponential form, that's what you're taking the logarithm of. So our output here is 1/9. So we would write log base 3 of 1/9. Again, listen to how I read that. Log base 3 of 1/9. That is not log of 3 to the 1/9 power. That's log base 3 of 1/9. Okay, and then what is log base 3 of 1/9? Whatever the exponent is what the logarithm should equal, -2. All right, for part B, 5 to the x power equals 125. This would be log base 5, because the exponential expression has a base of 5. Log base 5 of 125 equals the exponent, x. And last one, b to the x equals m. The base here is b, so this would be log base b. The exponential equation equals m, so we're taking log base b of m, and that should be equal to x, the exponent. All right, we'll practice more with this on the lab in just a second, but we should be able to go back and forth between exponential form and log form. This basic rule is going to be very crucial for the next couple of sections when we're solving exponential equations. All right, then next we're going to look at some properties of logs that will allow us to evaluate logarithmic expressions. There are lots of them. But on this list, we can start off with our first little definition that we just wrote. How do we go back and forth between log form and exponential form? Log base a of x equals y. That's equivalent to a to the y power equals x. That's our first rule. Okay, second rule. Let's think about what these logarithms mean. If we have log base a of 1, this is saying a to what power equals 1. So if I take anything, what power do I need to raise it to in order to get 1 as my output? That would be 0. Okay. Since a to the 0 power equals 1, that tells us that log base a of 0 is equal to, log base a of 1 is equal to 0. Okay. Second property, it's for solving something like log base a of a. This is asking, what power do I raise a to get a again? Well, anything raised to the first power is itself. So log base a of a would be 1. Next one, log base a of a to the x power. This is asking, what power would I raise a to get a to the x power? Well, x, whatever x is. If I want a to the x, I have to raise a to the x power. So log base a of a to the x would just be x. And this actually works out because the functions are inverses of each other. If you take the composition of two inverse functions, you get x. So the same thing would be true if we took a base of a and raise it to the log base a of x power. This also equals x. All right, so that's 1, 2, 3, 4, 5 properties we have so far. There are 2 more properties that I want to write down, and those 2 are about special bases that we have, base 10 and base e. So if we have log base 10 of x, we just call that log of x. So log of x is the same as log base 10 of x, but we don't write the 10 basically. And this is called the common log. So log base 10 has its own special notation, log of x. If you look on your graphing calculators, there's a button for it. Okay, and then the last one that has its own special notation is ln. ln of x, this is log base e of x. So instead of writing out log base e, we use the notation ln. And this one is called the natural log. All right, there are three more properties in a rule that I want us to write out here. The next 3 properties help us if we need to expand or condense a logarithmic expression. So the first one tells us if we have the log with any base of 2 terms being multiplied, we can expand this to the sum of 2 separate logs. So log base a of m times n is log base a of m plus log base a of n. So we can expand that to a sum of 2 different logs. The next one, log base a of m divided by n. If we have 2 logarithms, if we have the log of 2 terms that are being divided, we can expand this to a difference of logs. That would be log base a of m minus log base a of n. And the last property, which we will use a lot, log base a of m to the r power. If we have the log of a term being raised to a power, we can actually move that power to the front and multiply by it. So this would be r times log base a of m. Okay, this is how we can condense or expand logarithms. And we'll do a couple of examples with that. And we might as well put them all on one page. The last thing, a rule that we need to know for logs is the change of base formula. And the change of base formula tells us how we can take an expression written in any base and rewrite it in any other base. Usually we want to rewrite it though in terms of the natural log or the common log, so ln or log. But the change of base formula tells us that if we have log base a of x, and let's say we wanted to change it to base b instead of base a, this would be log base b of x divided by log base b of a. Or, like I said, in practice, we usually want to use base 10 or base e because we have a button for those in our calculator. So you can write it as log of x over log of a, or you can write this as ln of x over ln of a. All of these are true. You can change to any base. All right. Ooh, look at all these properties. We are going to go through. I like to write them all on one page so that we can see them all here at once. We are going to go through and do some problems where we evaluate exponential expressions by using these properties, condense and expand logarithms. I said exponential, I meant logarithmic expressions by using these properties. Condense and expand logs, and then use a change of base formula to evaluate some logarithms. All right, so write this down in your notebook. Put a big star by it. We'll refer to it a lot. All right, let's actually go back to our lab. And now we have enough tools to finish up problems 4, 5, and 6 from the lab. All right, so for problems 4 and 5 of the lab, you're just asked to rewrite the logarithmic equations in exponential form and then the exponential equations in logarithmic form. Notice here, though, that we have a couple that have log, the common log, which is base 10, and then ln, the natural log, which is base e. So let's talk about how we can use those in practice. All right, number 4, part A here. Log base 25 of 1 over 25 is -2. That is wrong. So this is not true. I think this is supposed to be a 5 here. There's a typo. This is supposed to be replaced. So let's fix this. Because when you write the logarithm in exponential form, you should get something that's true. All right, so this is log base 5 of 1 over 25 equals -2. This gives us 5 to the -2nd power equals 1 over 25. Okay, for part B, log of 1,000 equals 3. Notice how there's no little subscript written next to this log. So there's no base 5 or base 4 or base 2. There's no subscript written. If there's no subscript written, we know that this is the common log and our base is 10. Okay, so we have a base of 10. The logarithm is equal to 3, so our exponent should be 3. And then it's just telling us that 10 to the 3rd power equals 1,000, which is true. And then last one, this one might look a little funny, but this is what it means. We see ln. ln tells us that our base is e. And then the logarithm is equal to 5. So this is e to the 5th power. And then the term we're taking the log of here is e to the 5th. So the exponential form here would just be e to the 5th power equals e to the 5th power, which is true. Then let's go the other way for problem number 5. We want to write 4 to the 3rd power equals 64 in logarithmic form. The base here is 4, so we would have log base 4 of 64, and it should equal the exponent, 3. Log base 4 of 64 equals 3. All right, for part B, this is 10 to the -2nd power equals 0.01. This would be log base 10. Remember, for log base 10, that's the common log. So we just write log. You don't have to write the subscript of 10. Okay. We're taking the log of 0.01, and it should be equal to the exponent, which was -2. And then last one, 16 to the 1/2 power equals 4. This is saying log base 16 of 4 equals the exponent, which was 1/2. And we know that this is true also. All right, so again, going back and forth between log form and exponential form is going to be very, very, very important for us. All right, now for 6 and 7, we're going to use some of those properties that we just wrote down to evaluate the logarithms in number 6, and then to expand the logarithm in problem 7. So for number 8, we have log base 8 of 8. When you're evaluating a logarithm, always remind yourself of what this means. This is asking us, if I have a base of 8, what power do I raise it to get 8? So if it's helpful for you, if you're like a more visual person, you can say that, oh, this equals x, and then write it in exponential form. 8 to the x power equals 8. Then it's easy. We know that 8 to the 1st power would be equal to 8. So x should be equal to 1. So what does this tell us? Log base 8 of 8 equals 1. And we have a property, if you look over our properties, that tell us that this is true too. log base a of a equals 1. If your base is the same as the number that you're taking the logarithm of, your answer will be 1. All right, next for part B. So I should say for these problems, after you do enough of them and you kind of really understand how logarithms work, you might be able to do these without writing down many steps, and it's fine. You can ask yourself the question, log base 2 of 16. What does this mean? This means if I have a base of 2, what power would I raise it to get 16? So basically, 2 to what power is 16? Some of you may know that without having to write down all the steps, right? But in the beginning, it's kind of tricky to really understand what this means. So we'll say log base 2 of 16 is x, and then we'll write this in exponential form. 2 to the x power equals 16. All right, and then you'll remember, because we know our powers of 2, that 16 is the same as 2 to the 4th power. So looking at our exponents here, this tells us that x has to be equal to 4, or log base 2 of 16 must be equal to 4. All right, next one. Now, this might not be very obvious, but we have a property that says log base a of a to the x equals x. Part C is actually a problem where we use that property. Remember, ln is log base e. So this is saying we have log base e of e to the 7th power. The answer should just be 7, okay? So that's one way to think about it. Or if you didn't recognize that, let's say we did this the same way that we did the other ones. Set this equal to x. Remember, ln is base e. So this would be e to the x power equals e to the 7th. And then here it's clear that x would be equal to 7. So ln of e to the 7th power is just 7. All right, and last one here, log of 100. Log of 100, we have log, that's base 10. This is asking 10 to what power equals 100? Well, we know that 100 is 10 squared. So that must mean that log of 100 is 2, because it's the exponent we need to raise 10 to get 100. All right, so for some logarithms, nice ones like this, we are able to solve or evaluate the log without needing a calculator at all, okay? Not all logarithms are solved that nicely and easily. On our next lab, we'll see that. That's where the change of base formula comes in. All right, last problem from this lab. We want to use properties of logarithms to write log of x cubed over y to the 9th in terms of log of x and y. So instead of log of x cubed, we just want a log of x. And instead of log of y to the 9th, we just want log of y. So in order to do this, we're going to use the properties where we condense and expand logs. First, if we have the log of 2 terms that are being divided, so we have x cubed over x to the 9th, we can expand that to 2 separate logs that are being subtracted. So this would be log of x cubed minus log of y to the 9th. All right, that's step 1. And then from here, remember, if you're taking a log of some term raised to a power, we can bring that power down and multiply by it. It's the power property of logarithms. So log of x cubed is the same as 3 times log of x. Similarly, log of y to the 9th is the same as 9 times log of y. And then we are done. This is actually our answer. We started off with log of x to the 3rd over y to the 9th and ended up with something that's in terms of log x and log y. And just over here to the side, I'll show you the properties we used. We used the fact that log base A of m over n is log of m minus log of n base A. And then we used that log base A of m to the r power is r times log of m. Those are the two properties we used. All right, so this wraps up actually lab 5.1 and 5.2. There's another lab 5.2 for today's class that we're going to look at next. I'll do a couple problems from this lab, and then I'm going to leave the rest for you to practice on your own. But I just want to go through the types of problems that we see. For problems 1 and 2, we're asked to either condense or expand a logarithm. For these two problems, you're going to use the properties log of m, times n equals log of m plus log of n. Log of m divided by n equals log of m minus log of n. And log of m to the r power equals r log of m. You're going to use these three properties to expand or condense the given logs. For number 1, you're starting off with something that's condensed. And when we say that a log is condensed, I mean that it's just one logarithm, one log of lots of terms. And then you want to expand it to the sum or difference of several logs. For problem number 2, you're going to start with something that's expanded. We have the sum or difference of several logs, and we want to write it as one log. Okay, and we're going to use those three properties to do it. For part 3, this is where the fun happens. You want to use all of those properties of logs that we learned to try to evaluate all of these logarithmic equations, or expressions, I should say. And then for number 4, you're asked to use the change of base formula, which is log base A of x equals log of x over log of A, or ln of x over ln of A. Use this formula to evaluate these logarithms, and you'll need a graphing calculator for this. All right, I'll do a couple of these problems just to show you how to get started on each type of problem, and then, oh, there's also one word problem at the end that I want you to try. And then I'll leave the rest for you to practice for your yourself. For number 1, for this problem, you'll do it exactly like the last problem that we just did, where you expand into a subtraction and then bring down the powers. I'll leave that one for you to do because we did one similar to it. For problem number 2, we're going to go the other way. Use the properties of logarithms to write 1/3 log of A plus 3 log of B minus 5 log of C as one single logarithm. First, using this third property, if there's a number up front being multiplied by your log, you can move that up to an exponent. So log of A, 1/3 log of A would be log of A to the 1/3 power. 3 log of B, that would be log of B cubed. And then minus 5 log of C, that would be minus log of C to the 5th. So we're condensing them. Instead of having that number being multiplied on the outside, we're going to write it as an exponent. All right. Excuse me. For our second step here, notice we have two logarithms that are being added. This first property tells us that we can condense that to one logarithm and multiply the terms that we're taking a log of. What I mean by that is, instead of log of A to the 1/3 plus B to the log of B cubed, we just write this as one log, and then it'll be of A to the 1/3 times B cubed. Okay, and then we still have minus log of C to the 5th. And then the last step here, to take care of the two logs that are being subtracted, we can condense this into one log and divide the terms that are in parentheses. So this would be log of, we still have A to the 1/3 power times B cubed, but now it's going to be divided by c to the fifth. If you wanted to, you could write that a as the cubed root. So you can write this as a, or log of the cubed root of a times b cubed over c to the fifth. Either one is fine. But we took something that was written as the sum and difference of 3 different logs, and we were able to condense it to just 1 log. Problem number 1, I'm leaving for you. You're going the other way. So you'll start off by breaking into a difference, and then break it to a sum for the first 2 terms, and then bring down your exponent. All right, and then problem number 3. Look at all of this fun. I'm going to do a couple of them for you. But I'm going to leave most of them for you to do. So I'll do B, I'll do F, and I'll do D, because I think we already did that one. Okay, so B, D, and F. We want to evaluate these logarithms. Remember, you can think of this as like, what does this log mean? Log of the square root of 1,000. What is that even asking me? This is asking, if I take 10 as my base, what power would I raise it to get the square root of 1,000? Okay, for this one, before we start, we can use some properties of logs to rewrite this a little bit. The square root of 1,000 is 1,000 to the 1/2 power. And then we can bring that 1/2 down. This would be 1/2 times log of 1,000. All right, so log of 1,000. I'm going to come up to the side here. For log of 1,000, let's say that equals x. This is saying 10 to the x power equals 1,000. Oh, that's the first one. Sorry, that's part A. I'm writing it here, so I might as well write it. This is saying 10 to the x power equals 1,000. We should know that 1,000 is 10 cubed. So this is saying that log of 1,000 is equal to 3. Okay, we need that for the second one also, right? So if we have 1/2 times log of 1,000, this is just 1/2 times 3, which gives us 3/2. So the first one, log of 1,000 is 3. Then log of the square root of 1,000 would be 3/2. Part C will be kind of similar to that, except you have a 1 over 1,000, so you should have a negative exponent. So think about that. For part D, log base 3 of 1/9. I'm going to set this equal to x. This is saying 3 to the x power is 1 over 9. Okay, remember 1/9, well, 9 is 3 squared, so 1 over 9 would be 3 to the negative 2nd power. So x must be equal to -2 here. And that tells us that our logarithm, log base 3 of 1/9, is -2. And then part F, I wanted to do this one because I don't think we talked about this explicitly today. We talked about it in the last class. But for logarithms, we cannot take the log of a negative number. So log base 4 of -16, let me just show you why. This is saying 4 to what power equals -16. It is not possible to take 4 and raise it to any power and get a negative number. So this is no solution, because it's not possible. You cannot take the logarithm of a negative number. All right, I am going to just do one more, one of the change of base problems. And for these, you will need your calculator. And notice I have or here. I have it written in terms of log and in terms of ln. You can use either one. It doesn't matter, you'll get the same answer. So for part A, first, this looks like the problems we did in the last section. Why do we have to use change of base here? Well, for log base 3 of 15, this is saying 3 to some power equals 15. Now, if I scroll up a little bit, I had 3 to the x power equals 1/9. That one we were able to solve by hand without our graphing calculators, because 1/9 is a power of 3. It's 3 to the negative 2nd power. Here, 15 is not a power of 3. So we're not able to solve this one without a graphing calculator. We need the change of base formula. All right, so using change of base formula, log base 3 of 15, we'll say that this is equal to either log of 15 over log of 3. Notice we started off with one logarithm, and then we're having that is equal to the quotient of 2 logarithms. Or you can write it as ln of 15 over ln of 3. Either one, the only thing you have to be consistent with is if you use log in your numerator, you have to use log in your denominator. If you use ln in the numerator, you have to use ln in your denominator. And then from there, you pick which one you want to use. Get your calculators out. On the left-hand side, you'll see next to the 7 and the 4, the ln or log button. Use either one of them. When you type it into your calculator, it'll look like log, open parentheses, 15 divided by log, open parentheses, 3. Let's type that in. Log of 15 divided by log of 3. It's 2.464497, so 2.465. That is your answer. And I'm running out of space here, but I do want to talk about what this means. So if log base 3 of 15 is, I'm going to say it's approximately equal because I'm round, approximately equal to 2.465. What does this mean? This is telling us that if we take 3 and raise it to the 2.465 power, we should get 15. So as you're doing these problems with logarithms, always go back to, well, what does this mean, to make sure that your answers make sense. If I take 3 and raise it to the 2.46 power, I should get 15. And then I know that my answer is correct.